Section 6.5, we're going to find the average value of a continuous function. Now, you're probably used to averages from just everywhere, really. So to find the average of a bunch of numbers, you would just add them up and divide by n. So in this particular case, this is like the finishing place of an elite marathoner. You average it up, or you add them up, you get a total of 77, and you divide by 11, and the average finishing place is 7th. Which doesn't really feel good because, you know, he never finished 7th. You got that 56 in here. Basically, what that's showing you is that the average can be sensitive to outlying values. If you get rid of that, high finishing place of the 56, maybe he hit the wall because he's running his marathon, you get something much more meaningful. Now, there's a lot of different averages, a lot of different things you can call average. There's a harmonic mean, a geometric mean, root mean square, etc. But we're going to focus on what it's like to find the average in terms of a continuous valued function. So that's going to be a little bit more challenging. Mostly what it refers to, what it's going to boil down to, is an excuse to find an integral. So what are we going to do to find the average value of a function? Well, we have to add up all the values of the function. And if this was a nice finite list, you could add them up, that'd be great. But when you have a continuous function, the way you add up all the values is with an integral. So it's going to be the integral of f of x dx. But then you have to divide by n. Well, our dividing by n in this case is really multiplying by the reciprocal of the length of the interval. So 1 over b minus a. So, okay. So it turns out to be kind of an area problem, really. And let's do a few examples of that. We'll start with this function, y equals the square root of x. So, example A. And we're going to look at that on the interval 0 to 4. So, okay. So y equals the square root of x on 0 to 4. So let's take a look at what it looks like graphically speaking. So, wrong one. Still wrong one. There we go. There's the right one. So we want to find the average value of this function. Now this function passes through an infinite number of values as it starts at 0, gets all the way up to 2. So what's the average value? Well, you kind of got to weight it. And fortunately for us, that's done by our integral. So to find the average value, so average value is going to be the integral from 0 to 4 of the square root of x dx. But then I'm going to multiply by the reciprocal of the length of this interval. So it's 1 over 4 minus 0. Now, if you're stuck doing this by hand, you'd probably do a couple things. First of all, write that as 1 over 4. The integral between 0 and 4. What other change would I make to my integral? Perfect. X to the 1/2. So that's going to be 1/4. And then x to the 3/2 divided by 3/2, evaluated between 1 and 4. Maybe not a bad idea to clean this up a little bit. 1.5 times 4 is going to be 6. So I'll do that as 1/6. 0 to 4 of x to the 3/2, or 1/6. 4 to the 3/2 minus 0 to the 3/2. And that's going to be 1/6 times 4 to the 3/2 is going to be 8. 8 over 6 reduces to 4/3. So, yay, not so bad. Like I said, more or less just an excuse to have you integrate. So, nice, nice. Kind of a friendly one to start with. How are we looking on that one? All right, not so bad, not so bad. Questions on that one before we do second example? Eli, doing okay?
Yep.
All right, thank you. Let's take a look at it graphically before I move on, because I do have some nice graphs associated with this. So what we first found was the area right here underneath our curve, and then multiplying by the reciprocal of the length of the interval. So multiplying by 1/4, that's going to turn that area into an average value. So looking back here, our average value was 4/3. So, okay, great. So it really kind of gives you two ways you can think about finding this area here. One is you could just integrate the original function and find the area underneath the curve. Or if you had the average value of the function, let's shut this off, shut this off. What we could do is just find the area in this rectangle. Those two are the same thing. So nice, nice. And you can see that the average value is going to be, what would that be? 16/3 divided by 4 gives you your 4/3. So, all right, let's try a next one. So the next one is this function, 6x sine, 6 sine x minus 3 sine of 2x. And let me scale this down a little bit, fit that all in. So, all right, let's do example B here. So once again, we got y equals 6 sine of x minus 3 sine of 2x. And that's on the interval 0 to pi. So 0 to pi. So again, kind of a friendlier problem. We're going to take and integrate this function, 6 sine of x minus 3 sine of 2x. That's going to be between 0 and pi. Let's not forget the dx here. I do want to see that dx term. Dx. There's one last thing that I need. What is it?
1/b minus a.
Yeah, 1/b minus a. In this case, 1/pi minus 0. Let's just put 1/pi. Now, in this case, maybe you want to break things up. It's kind of up to you. You got that 1/pi times this. That's going to be 1/pi times the integral from 0 to pi of 6 sine of x dx minus, and we got to be careful here because that 1/pi has to distribute itself, minus the integral from 0 to pi of, I don't know if you want to put the 3 out here or not. I'll just keep it in here. 3 sine of 2x dx. Now, can anyone suggest to me why I bothered to split it up like that? Yeah. Here, I can just integrate this directly. All right? It's just 6 sine of x. Take the 6 out. We know what the integral of sine of x is. Sine of 2x, well, that's a little bit more of a problem. If it was sine of x, we'd be in great shape, but it's not. It's sine of 2x. So here, you kind of have to make a u substitution. Now, I'll be honest with you. In Calc 2, I start encouraging my students to be able to more or less do this stuff in their head to get the antiderivative, kind of circumvent all that extra work of having to practice and work through a u substitution. That said, I am going to practice a u substitution here because this is Calc 1 and we need to practice. Let's take the 6 out here, 6/pi times the integral from 0 to pi of sine of x dx minus, I'll take the 3 out, it's going to be 3 times 1/pi, the integral from 0 to pi of sine of x 2x dx. Like I said, this one you can do directly. Nothing wrong with that.
Why is it 3/pi? Was it because you like?
Well, two things happened. The 1 over pi distributed itself, and it took the 3 out.
Okay.
So, appreciate the question. But it's this one that we're going to need to do a little extra work for. Let's finish up this one. That's going to be 6 over pi times, well, what's the antiderivative of the sine function? Negative cosine. So 0 to pi of negative cosine of x. I don't need anything else, no dx there, so all right, that's good. Now over here, we're going to have to do a little extra work because we don't know the exact antiderivative of this without maybe doing a u substitution. So what am I going to let u equal? 2x. And then du equals 2 dx. I'm skipping a step there. It's du by dx equals 2. And then multiply both sides by dx. Let's change our units of integration. So I want to know what happens when I plug in a 0 and a pi. U of pi is going to be 2 pi, and u of 0 is still going to be 0. So my new limits of integration are going to be between 0 and 2 pi. All right, so minus 3 over pi times the integral from 0 to 2 pi of sine of u du, well, I've got a dx. What's du going to equal? Or dx going to equal, I should say.
1/2 du.
Yeah, 1/2 du equals dx. So those are interchangeable now. Du, 1/2 du and dx. So I'll do 1/2 du. That 1/2 can come out in front. Yeah, I know. It feels like so much work to do that little bit. I know. Maybe after the end of this, I'll talk about what you can do here. That's going to be 6 over pi times negative cosine of pi minus negative cosine of 0. So it'll be plus cosine of 0. Have you already figured out what's going to happen on that second integral? So that'd be negative of negative 1. It's going to be 1 plus 1 minus whatever this turns out to be. So that's going to be minus 3 over pi. Let's bring the 1/2 out front. 1/2. Now I need an antiderivative of the sine of u. Antiderivative of the sine of u is going to be minus cosine of u. The nice thing about switching our units of integration is that I don't have to switch back. I don't have to go back to units of x and the integral from 0 to pi. I can just finish this off in units of u. The negative times a negative becomes a positive, so that's going to be a plus 3 over 2 pi times cosine, minus cosine of 2 pi, minus cosine of 2 pi, minus another minus, which becomes a plus cosine of 0.
Where'd you get the negative times negative so that became positive right there? The 3 over
Here?
2 pi? No, the 3 over 2 pi. How come it?
Oh, you know what? I took the negative out, so let's see, negative. You know what? This should be a positive, and this should be a negative. Thank you. And I think Caitlin's seeing what happens here. And it's really frustrating, especially after the work we did on that second integral. Go ahead, Caitlin, spoil the
All
fun.
good, just one.
No, it's all right. What is it? What does this equal?
It's 1 minus 1,
Yeah,
which is 0.
1 minus 1. So all that work literally for nothing. because that second integral ends up to be 0. This is a 2 times pi over, or times 6 over pi. So we end up with 12 over pi plus 0, or 12 over pi. Wow. Mia.
Because like you just had a 0 and you did all that just to get that.
Yep.
Is there a way to like not do that?
Yeah, you have to be good. I guess the way we could have avoided that is if we had looked at the graph and realized that part of this graph is below the x-axis and part of it is above the x-axis, and they perfectly cancel each other out. But unless you're willing to take the time to do that, you just don't know.
Does it have anything to do with like framing an odd number?
No, it just has to deal with the fact that, you know, part of it's below the x-axis and part of it's above the x-axis, so that those cancel each other out. Let me see if I can't pull up a quick graph here, and I know I got another question. Let's see, Desmos. Yeah, let's learn together. All right, so y equals sine of 2x, and let's focus in on that on the interval 0 less than or equal to x less than or equal to pi. So it's exactly what happened, is that part of this integral is above the x-axis and part's below the x-axis, and so when you add up those areas, they're really signed areas and they cancel each other out. True?
So that's not an odd function.
It's not the odd function rule. Odd function rule, keep in mind, for the odd function rule to apply, you'd have to have a symmetric interval. So you'd have to be going from like negative pi to pi, or negative 2 to 2, or something like that. So yeah, it doesn't have anything to do with the odd function rule. It just has to do with the fact that these two areas, you know, are opposite but equal. Okay, good questions. Now, here's what I do for myself, especially in Calc 2, because in Calc 2, you kind of have to get through a lot of this stuff a lot faster. You're not going to be spending all that time on this. So let's think about differentiating sine of 2x. If you differentiate sine of 2x, then you're going to have to use the chain rule. What would we end up doing? You'd have cosine of 2x, and then what? Somebody said it.
Times 2.
Times 2. So you got that extra concept of times 2. But integration is the opposite operation of differentiation. So instead of a times 2, what do you think we'll get? Divide by 2. So if you revisited this and said, all right, well, that's going to be negative 3. I'm going to have that constant of a 1/2, because instead of multiplying by 2, I'm going to divide by 2. It's going to be 1/2, and then 0 to pi. So I've taken care of my constant. The antiderivative here is going to be minus cosine of 2x. Great. Those negatives cancel. You end up with 3 over 2 pi. And then the cosine of pi minus a cosine of 0. Let's see, does that work out right? Something, I'm off by a factor here.
Should be 2 pi.
2 pi. Yeah, to be 2 pi. So this would again be 1 minus 1, which is 0. So you're doing things in the original variable of x. If you can do that mental gymnastics, it's a lot faster than doing the u substitution. But it depends on your comfort level. You know, some people just have to do the u substitution. So, all right, good question. Anything else on that one? Let's see. So the average value, here's your average value. Your average value should be somewhere in the middle, like that. So, there you go. All right, and the screenshot that applied last semester. Sorry, I'm not doing it this semester. Let's do another one. So kind of a really short function. Let's see.
I have a question.
Yes, Tony?
I did a screenshot before, and I was just wondering if you gave the credit for those.
I haven't done that. As long as you post it on D2L, it's still there. All right, so let's look at the function. This is example C. The function is y equals 2x e to the negative x squared. And we're going to look at that in the interval 0 to 2. Okay, great. So let's see, we want to find the average value of this function. Now, not everything has to start at an interval of 0 to something. It could be, 1 to 6, could be whatever. But in this case, the average value can equal 1 over 2 minus 0. And I'm only putting in that minus 0 here to remind you that it's the length of the interval. 0 to 2 of 2x e to the negative x squared dx. Now, e to the negative x squared is kind of an interesting term, and we'll look at something like this in just a minute. But for now, we need to integrate this. Suggestions. What were you going to do to integrate that one? Yeah, use substitution. Use substitution because this is not something we can find an antiderivative of. So you're going to have to trick your integral. Pranav, any suggestions? What could I let u equal?
E.
E would be just a constant, and so derivative would be 0. Negative x is close. Some help? Yeah, let's do negative x squared. Now, the thing about a u substitution is that when you decide on u, then eventually you have to differentiate this, right? What happens when I differentiate a squared term? What am I going to get? Yeah, I'll get a minus 2x. I'll get something to the first power. The thing that you should notice is that if that's a 2, this is a 1. And so when I differentiate something with a power of 2, I get something with a power of 1. It's nice to see that derivative in here, at least in some form. So du by dx equals negative 2x. So I'm actually showing all the dirty work this time. Differentiate, and then multiply by dx. And take a look at what we've got in our integrand. So let me rewrite it. It's going to be 1 over 2. The integral from 0 to 2. And let me write it that this e to the negative x squared times 2x dx. Why did I rewrite it like that? So 2x dx there, 2x dx here. The only thing I'm missing, and I'm not sure if you quite heard Rob or not, or excuse me, William, but there's a negative here and there's not here. So I'll get rid of it. I'll divide both sides by negative 1, 2x dx. Let's change our limits of integration at the same time here. I'm just going to get rid of the problem in x and turn this into a problem of u. So, all right. So I need to evaluate u at a couple places. I need to evaluate u of 0. Let's get this. U of 0 and u of 2. So let's plug it in here. 2 times, it's going to be negative 0 squared is still going to be 0. Negative of 2 squared. Am I going to get 4 or negative 4 when I plug in the 2 here?
Negative 4.
Negative 4. Okay. Let's change everything up. Let's see. Minus du is going to be 2x dx, so I can substitute that in here. So 1/2 the integral from 0 to negative 4 of e to the u times minus du, like that. Are we okay with our u substitution? Gucci? Looking good there? I'm going to take the u out in front and do minus 1/2 integral from 0 to negative 4 of e to the u du. Is there something about this that bothers some of you maybe? That last integrand? What's unusual is that the upper limit is bigger, is less than the lower limit. Usually we go top to bottom, bigger to smaller, but it's not the case in this case. Let me remind you or tell you of one of the properties of integrals. If I switch the order, and I know in your heart of hearts you're like, no, that just looks wrong. Let's do negative 4 to 0. You can do that. But what it does is it changes the sign of my integral, or of my answer. So instead of a negative 1/2, negative a negative becomes a positive 1/2. E to the u du. It's a nice little trick if you want to use it sometime. I don't think there's a problem where I'm going to require you to use it, but I'm glad you're aware of it. Last but not least, the integral from negative 4 to 0 of e to the u is going to be the 1/2 e to the 0 minus e to the negative 4, or 1/2 of 1 minus 1 over e to the 4th. Now your calculator can get you that, can get you this answer, but it's going to be a numerical answer. It's not going to be a nice decimal answer. Okay.
So if we don't choose to write the way you did it, then should we just put a negative there? You're the one negative 1/2.
Yeah, if you didn't change up the limits of integration, here's what would happen. When you come down here, you'd have a negative out here, but these two would be in the opposite order. It'd be e to the negative 4th minus e to the 0, and you know, basically this would be opposite of what this is, but then you'd have a negative out here, so it'd still balance out. So yeah, it works either way. This is the right answer. Now, for whatever reason, it's a lot of times very easy for people to forget that they need this constant out in front here to get the average. It's just an easy thing to forget. Let's take a look at what happens if you maybe forgot that. So you get your average value, but you forgot that constant out in front there. Let's take a look at what the average value would look like. Can anyone tell me what looks wrong there?
It's above the graph.
Yeah, it's above the graph. The average value should be some value in between the top and the bottom. And it's not. It's bigger than everything else. Kind of reminds me of a politician one time. He said, oh, I'm looking for a society in which everybody makes above the average wage. Well, you can't. By definition, above average, you know, or average means that there's going to be some above and some below. You can't all be above average. So, in any case, if I turn on that constant, that looks a little bit more reasonable. So, yay. Now, I said I was going to make a little bit more remarks about this. Well, let me take the occasion to do so. Let's see, I can get rid of this one. Yes. And there's been a lot of kind of extreme weather events this summer that we've seen. So You know, I'm not going to look too far outside of the state of Michigan. I got a really cool data set here, and it shows me the average monthly temperature for every month of the year, going all the way back to 1895. And that's for all 83 counties in Michigan. So kind of cool. And what I did is I calculated the mean and what's called the standard deviation of all this data for just the month of July. I wanted to kind of take a look at it in July. So let's see, where's my graphs? There we go. So if you were to look at just the actual data, here's what it would look like right there. So that's a histogram. You'll study that kind of stuff in statistics, along with what's called the normal distribution. Now, the normal distribution is a lot like what we just dealt with. So if you look at the curve that plots out the normal distribution, it'd be y equals 1 over the square root of 2 pi times something called sigma, which is your standard deviation. And, not quite there. So y equals 1 over the square root of 2 pi times sigma, e to the negative 1/2 of x minus mu over sigma squared. Kind of a gnarly looking function, but this is what traces out the normal curve or bell curve. And actually a name that you're familiar with in this class is Gauss. Sometimes, I mean, maybe you run into somebody that calls it a Gaussian curve, but it describes a lot of natural phenomena. So looking back at this, here's a normal distribution, but you can change things. You can change the mean, which changes the location of this, and you can change the standard deviation. Remember during the pandemic, the big slogan was to do what with the curve? Anyone? Flatten the curve. Basically, they wanted to spread things out, which means you're increasing the standard deviation. So, for this curve, let me plot a normal curve with the appropriate mean and standard deviation. Now, I could try and find the average value of this and stuff like that, but I want to focus on something else a little bit, and that is some of these extreme weather events. It's unusual to get an average temperature for the month of July in Michigan up here in this range, like 76 or greater. And the average value here, or excuse me, the probability that it happens is really just the area underneath that curve. Now this summer we've seen a lot of different extreme weather events that, based on this curve, just shouldn't happen. They should be very unlikely. But that's assuming that this curve has remained unchanged. What could happen, though, is that maybe the curve is being shifted. And so that if you were to shift things, if that curve is being shifted over, what's happening to that area underneath the curve? It's increasing. So the likelihood of these extreme events is going up. So that's kind of a calculus / statistics look at some of what we've seen maybe this summer. All right, let's do one more here. What's nice about this one is we're at least moving away from the interval 0 to whatever. So our last example here is we're going to try and find the average value of the function y equals x squared between, or y equals x minus 4 squared between 3 and 6. So example.
Go back to example C really quick.
Did you need to?
I just need to look at something towards that.
Good there?
Yeah.
Okay. All right, so example D, y equals x minus 4 squared between 3 and 6. So see if you can't set up the integral. What integral are you going to calculate to find the average value here? So what's the integral? What expression should I write down here?
1/2.
All right, so 1 over
6 minus 3.
6 minus 3.
Integral 3 to 6.
Mm-hmm.
Yeah.
Nice. So if you're stuck doing this by hand, then you've got one of two choices here. So that's going to be 1/3 integral from 3 to 6 of x minus 4 squared dx. You can either expand that and write it as 1/3 the integral from 3 to 6 of x squared minus 8x plus 16. I hope and trust that no one's going to expand that as x squared minus 16, right? That wouldn't happen in a calculus, right? Right. All right, just play along with me. You also could, if you wanted, and sometimes it makes sense, you can make a u substitution here, and then, it might be a little bit of an easier problem. There's nothing wrong with making a u substitution. In particular, kind of going back to what I said about the u substitutions with problem B, kind of do those things in your head. If you did a u substitution to be u equals x minus 4, and the interesting thing is du equals dx. Those are particularly nice u substitutions when that happens. So I can finish it up with a u substitution here or on the graphing calculator. Your choice.
So when I did the u substitution and I did like u 3 over 3.
All right. So 3 to 3, 3 to 6. So at u equal, let's see, we're going to have u of 3 would be -1, and u of 6 would be 2. So I guess I got to get rid of my limits here. Change those up. So it's going to be -1 to 2 of u squared du. And like I said, the nice thing about this is that when du equals dx, your u substitutions are very, very user-friendly. That's going to be 1/3 u cubed over 3 between -1 and 2, or 1/9, -1 to 2 of u cubed. So 1/9, 2 cubed is 8, minus -1 cubed is -1. So, wow. I think we're going to get a 1. Nice. Comments on that last one? All right. Do you need a review of FNInt, or are you guys pretty good with FNInt? Good with that? All right.
What?
Let's see. Average value. Let's shut these guys off. And that one on. There we go. So it looks kind of odd. It feels odd to me that 1 is the average value, but well, that's the math.
That one quick.
All right.
Did something wrong.
Comments or thoughts on this one? Yes.
Can you just go back to that example and do the last part?
Yeah.
I think I'm good.
You're good? All right. Anything else? Nice. Good luck with this section.